Okay, class, this is where we start, right? We talked about the work done can be positive or negative, depending on uh, whether the energy increases or decreases. When you do work, we can either increase the energy of the system that you are doing work on, or we can extract the energy out of the system, then the work done will be negative. The mathematical sign of the work is positive when the work is done on the system. So you increase the energy of the system. Otherwise, if you extract the energy out of the system, then it is a negative work. So we say work is done by the system. So it will lose energy. So I showed the example of, an object is, say, moving. Okay, let's look at this. So here you are pushing an object within a force to the right, and the object has a displacement also to the right. So the angle between them is 0. Cosine 0 is 1. Then you got positive work. But suppose an object already has some speed and is going to the left, and you are applying the force to the right. And maybe let's say it has some speed, say 10 meters per second. It is not going to stop immediately, although you're pushing it in the opposite direction. It is going to travel a certain distance, let's say after moving some displacement. The displacement is now going to be to the left. So it maybe it will become, say, 5 meters per second. So the kinetic energy has decreased. The energy has decreased now. So you can also see that the work done is negative, because work done is given by FD cosine theta. It's a scalar product of the force and the displacement. So that's why the cosine theta comes in. F is a magnitude, D is the magnitude of the displacement. So cosine theta can bring the sign into it. Theta here is equal to what? The force to the right and the displacement to the left. What is the angle between force and displacement? 0. Any other answers? Let me see. You should say this is the displacement vector. Look at the direction. You have to bring them tail to tail, right? And this is the force vector. So if you bring tail to tail, that means, okay, let me redraw this. So the tail here. Can you answer now? What is the angle between F and delta R? 180, yeah. Okay. All right. So if it is in the same direction, it is 0. If it is in the opposite direction, the angle is 180. Okay, good. Ariam, thank you. So that's how it becomes negative, because if you substitute 180 here, cosine 180 is equal to what? Anybody knows what is cosine 180? If you draw a graph of cosine theta versus theta, at theta equal to 0, it is +1. At theta is equal to 90, it is 0. Then at 180, it becomes -1. All the values of theta from 0 to 90, it is positive. It start from 1 when cosine 0 is 1. Then as the angle increases, it becomes less and less. At 0 degree, at 90 degrees, it becomes 0. Then as it increases from 90 to 180, it becomes more and more negative. And at 180 degrees, it becomes -1. Okay. So you see that any angle greater than 90 degrees, the work done will be negative. Less than 90 degrees, the angle between force and displacement, it will be positive. So you can have a negative work and a positive work. But it doesn't mean they are vectors. Work is not a vector. Work done is not a vector. It's a scalar, but it can be negative. So now we come to define the kinetic energy. We already told what kinetic energy is, what potential energy is, introduce them. Kinetic energy, we said, it has something to do with the speed. If something is not moving, it has zero kinetic energy. If it is moving, it has a kinetic energy. So mathematically, this is the definition of the kinetic energy. It is a simple definition. If something has a speed, we actually hear the speed, okay? Speed, the magnitude of the velocity. So the kinetic energy is simply the half multiplied by mass of the object multiplied by the speed of the object square. That's it. So if you look at the unit, it is going to have the unit joule, same as the unit for work. See, m is kilogram and speed will be squared will be meters. It is the same as Newton meter, which is the work done, the unit for the work done. Because Newton is kilogram meter per second squared into meter, so you will get kilogram meter squared second squared. That is joule. So the kinetic energy has the unit joule. It is the energy stored in the speed of an object. More speed mean it has more kinetic energy. Less mean less kinetic energy. Okay. Also, it depends on the mass. Right. Now, this gives us a nice theorem called work kinetic energy theorem. Now you understand with my example of pushing an object, the example we saw before. When you have the force and the displacement in the same direction, it is a positive work and the kinetic energy increases. If it has a zero speed here it will have a greater speed, okay, more than zero. So the kinetic energy increased. In this case, it has a zero, it has some positive kinetic energy, but you're applying the force in the opposite direction to the displacement, kinetic energy decreases. So it gives you an idea for a law or theorem. The work you do on an object, you may have many work from different forces. So the network will be equal to the change in the kinetic energy. Okay, net in the sense, there can be more than one work. One of the work is, increasing the kinetic energy. One other one is decreasing the kinetic energy. So we take the network. Suppose the network is positive, change in the kinetic energy will be positive because the network is equal to change in the kinetic energy. It's a very simple formula, okay, theorem, but it is powerful at the same time. So with using this, we can solve many practical problems. So is that clear, everyone online? Do you understand this work kinetic energy theorem? The amount of work you do on an object will change its kinetic energy. Okay, very good. If the network is positive, change in the kinetic energy will be exactly the same amount and positive. So you can see the kinetic energy will increase. If the network is negative, the change in the kinetic energy will be negative. That means the kinetic energy decreases. Okay. This is work kinetic energy theorem. The net work is the sum of the work done by all the forces acting on the object, and delta K E kinetic is the change in the kinetic energy. Sometimes you write the kinetic energies like this. Sometimes you also like this. So, it depends on the notation. So I'm going to use alternately. Sometimes I will use that and sometimes I will use that. So please don't get confused. Good. So now we have got a question. Concept question. Following slides show 5 plots of kinetic energy as a function of the velocity of an object or the speed. Which one is consistent with the mathematical description of energy? right? Let's see. Now, what is the equation for kinetic energy? Is equal to half m speed square. So this is in the y-axis, and this is v is in the x-axis, so it's x squared. It's v, not v squared. Okay. So some constant, let me call it a, because we are not changing the mass. Half is a constant. So the equation for a graph of y versus x, where the relationship between them is y is equal to some constant into x squared. That means if I draw the graph of kinetic energy versus v, that is y versus x, do you think it will be like this? No, because that's a linear, right? This is if the relationship is like this, x to the power 1, linear. So the relationship between kinetic energy and the speed is not linear. It is speed squared relationship. So this is also not correct. This means that it is linear again, but with this is negative. The slope is negative. And this means y is a constant. That's also not correct. It's not a constant. It is a function of x. So either this one or this one. Which one is correct? E, D, E. E, why not D? Yeah, you can see as x increases, y should increase, not decrease. And also when x equal to 0, y is equal to 0. So that is the parabola, right? So that's, probably, I don't know, we have learned this in your math, okay? A graph of y equal to x squared is a parabola shape, okay? Why don't you have negative values? Because speed is positive. We don't, speed is the magnitude of the velocity. It starts from 0 and okay, very good. Let's go. So that's the answer. So we define the kinetic energy. So let's define the potential energy now. We said for a conservative force, a class of force called conservative, gravitational force is an example. We can define potential energy. So let's define for the gravitational force. So we call it gravitational potential energy. Without going into the proof and so on, it can be proved with some calculus. We're not going to do that. We'll just give you the equation. The potential energy, sometimes written like that as well. So, either this or that is equal to mass of the object. G is the gravitational acceleration, which is 9.8 meter per second squared in SI unit, multiplied by y. Y is the vertical position. I have to stress this vertical position. I will explain that more. So that's what the gravitational potential energy. M is the mass of the object. G is the constant gravitational acceleration. We are talking about the Earth's gravitational force, multiplied by the vertical position of the object. So this gives the system, the Earth plus the object, the potential energy of that system. Now, okay, that's good. But why is the vertical position? From where do we measure it from? Where do we put the 0? The center of the Earth? No, I mean vertical position relative to the Earth, right? How above or below the, where do you surface of the Earth? Okay, right. Actually, it is not important. You can put wherever you want. Suppose you have an object on a table. For some reason, instead of the surface of the Earth, you can say y equal to 0 here. Then you will say the potential energy of this is 0 because you took the reference level to be at the level of the table. Okay, so for you, it will be 0 potential energy. So maybe you will differ. Okay, you will say, no, I want to choose a different point as 0. You may choose y equal to 0 at the surface of the Earth. Then y is not 0, right? For you, the y, let's say it is 10 meter or 1 meter high. So for you, the potential energy will be m into g into 1 meter. It is not 0. So it's up to you. Okay, you can choose wherever you want the y equal to 0 to be. Is that clear? People online? So I'm telling, okay, the potential energy is given by the equation mgy. Y is the vertical position relative to the Earth. Okay, good. So, but yeah. So we said that where do I put the y equal to 0? Because I need to put the y value, the y coordinate, only the vertical coordinate. So we need to define where is your y equal to 0. It is arbitrary. It's up to the person who is doing it. So one person will say, okay, I'm going to put it on the surface of the Earth. Then his y will be, say, 1 meter. But if you choose y equal to 0 at the level of the object itself, then the potential energy will be 0. Okay, so it's up to you. But we are not interested in the absolute value of the potential energy. We only care about the change in the potential energy. You will know why later. What is important for us physically is the change in the potential energy. We don't really worry too much about the absolute value of the potential energy. We are only always interested in the change in the potential energy. Therefore, I can get this equation. If E is equal to mgy, delta E will be mg delta y, because m doesn't change, g doesn't change. It is only the y that is changing. So change in the potential energy will be mg multiplied by change in the vertical position. Okay, because this is the quantity we are interested in, not the absolute value. And you should know the equation for the absolute value. Then I am writing the equation for the change in the potential energy. Okay, now the reason is now choosing where y equal to 0 does not matter now. Let me prove it. Why it doesn't matter. Let's say you have the y coordinate. The y should be measured upward. Okay, up is the positive. That's also important. Y is the vertical position, and the positive direction is upward. Okay, this is very important. So now, let's say you have 2 points, the initial and final. Let's say this is the initial and this is the final. Okay, and y initial, y final. It depends on where you put the 0. Let's say you put the 0 here, and let me say this distance is say 5 meter, and this distance is 10 meter. The height is, okay, only the height is 5 meter, and this height, so 5 plus 5 is another 5. If you put the y equal to 0 there, y initial is equal to 5 meters, right? And y final is equal to 10 meters. The coordinate where the object is initially, it is at the coordinate of 5 meters, and finally the object is at 10 meters. Someone else, he want to do things differently, and he is putting y equal to 0 here. Let's say here. For some reason, because maybe he is in a building, at a distance of, let's say 7 meters above. He is 7 meters above in a building. So he like to place the y equal to 0 where he is for some reason. It's okay. I mean, he can do that. According to him, and use the red, according to him, initial position is what? For him, the initial position is equal to, he is this much below from him, right? Do you know how much below this is? What is this distance equal to? If this 7 meter and this is 5 meter, it is 2 meters below. The initial position is 2 meters below him. So he will say y initial is equal to -2. Is that clear, Munira? He is at a height of 7 meter, and his initial position is 2 meters below him, because he is standing 7 meters above, and the initial position is 5 meters above the floor. That means the initial position is 2 meters below him. So according to him, y initial is -2. What about y final? According to him, this object is now 10 minus 7. 10 minus 7 is 3 meters. So for him, it is 3 meters above. Okay. So for the guy with the blue pen, okay, who is drawing everything in blue, initial position is 5 meters, final position is 10 meters. But for the guy who is standing 7 meters above and he is choosing the y equal to 0 there, according to him, initial is -2, final is +3. Okay, now let us get the delta y. According to the red guy, what is delta y? Delta y is equal to 3 minus -2. How much is it? 5 meters. Okay. According to the blue guy, delta y is equal to y final, according to him, is equal to 10. Y initial is +5. So it doesn't matter where you choose the 0. Delta y is the same. That means change in the potential energy will be the same. 15, Eileen. 10 minus +5. Yeah, okay, got it. Right. So my point here is what I am trying to tell you is we are interested only in the change in the potential energy. So when you want the change in the potential energy, you don't care where you put the y equal to 0. It doesn't matter. What I need is only delta y. What is the difference between the final position and the initial position? It doesn't change. It doesn't change where you put the y equal to 0, the reference level. Okay, so now we should be able to answer this question. A person states that an object of mass 1 kilogram, this 1 kilogram, has a potential energy of 0. Somebody just come out of the blue and he says, okay, I have an object and its potential energy is 0. He's just telling you. Now, with this information, can I answer this? No. Why? Where is the object located related to the Earth's surface? Why we cannot tell? The answer is we cannot tell where he is located, because I don't know where he put the 0. Okay, because it is arbitrary. Say, suppose the object is here. Okay, so what he does, he's saying it is equal to 0 because he put the y equal to 0 where the object is. So we have no way of knowing what where the location is. Okay, so maybe the object was on the ground. So he put the y equal to 0 on the ground. So we have no way of knowing actually where it is. So the answer is can't tell. Right. Now we come to an example. Let's say there is an object, a box, a green box, at some initial time. It has a coordinate, y coordinate, so the vertical position, y initial. Then we drop it, we release it. You know what happened? It will go down, right? So let's say it has a speed v initial, maybe 0. Okay, v initial. So it goes down, we observe it. After, say, time final at certain time, then we look at its position, let's say y final, and say it has a speed v final. Here v initial is 0. Let's say it's 0. V final is greater, right? I mean, if you take a real example, it will accelerate, it will have a speed when it comes there. Okay. What is the energy when it is here? If I take potential energy, if I take the y equal to 0 there, the potential energy will be, let me say, we will calculate using mgy. So m, let me put, say, 1 kilogram. G, for convenience, for calculation, I will call 10. Okay, it is not 10, but 9.8, is difficult to do the calculation. So convenience, I will say 10. And why? Let me say also 10. So what is the energy? 100 joule. 10 into 10 is 100. So the mass is 1 kilogram. I'm just taking some numbers. And G, let me take it as 10, okay, for convenience. Okay, it is actually 9.8, and 10 is a bit not accurate, no problem. So it has a potential energy of 100 joule. What about the kinetic energy? We are dropping from 0 speed, okay? So the kinetic energy is 0. Okay, right. So here, it is coming down. Now let's say it is 1 meter. Okay, now this is 10 meters from the floor. Now it is 1 meter. The potential energy is now what? Potential energy final will be equal to 1 kilogram. 10 into 1 is equal to 10 joule. Okay. Of course, the vertical position has decreased. So the potential energy has decreased from previous big value 100, small value 10. So it has lost potential energy. How much has it lost? 100 minus 10, 90 joule. Where did it go? Yeah, okay. Because initially it has a 0 kinetic energy. Now, it has increased kinetic energy. Now, if I ask you what is the final kinetic energy, you should be able to tell. That is called the conservation of energy, mechanical energy. It's kinetic energy plus potential energy. Imagine, assuming there are no other non-conservative forces like air, drag, friction, so it doesn't lose energy. So all the total energy of the object should not disappear. So I can say the kinetic energy initial plus the potential energy initial must be equal to the kinetic energy final plus the potential energy final. Okay, so this is called the conservation of mechanical energy. Okay, because we assume there are no other non-conservative forces like air drag, air resistance, friction, so it doesn't lose the energy as thermal energy or any other form. So then we can say we cannot allow the mechanical energy to change. So whatever the total mechanical energy before is 100 plus 0, potential plus kinetic, is equal to the total energy now, which is 10 potential plus the kinetic energy. Now you can find the final kinetic energy. This must be 90 to keep the balance. Okay, so we can use this technique, what is called the law of conservation of mechanical energy, to solve certain things. Okay, now let me do this and I will stop because, yeah, in the morning class, I had to spend a lot of time answering questions, so I couldn't go beyond this. So I don't want to, but if you have question, you can ask me. Let's look at this slide. So we're going to say the total mechanical energy, provided we have an isolated system. So we're talking about a system now. Isolated system, you remember what is an isolated system in the last class?
Energy constant.
No, but the way we define, nothing goes in, nothing comes out. No energy goes in, no energy comes out. No work is done on the system, so you don't flow, energy doesn't flow like heat energy. So isolated system, that means the energy of the system, because we are not doing work externally, it doesn't leak in or out. So I can say total energy inside. Also, another one, there are no non-conservative forces inside the system, so there is no internal losses as thermal energy, then we can say that total mechanical energy, kinetic energy plus potential energy remain constant with time. There may be kinetic energy may decrease, but it will be balanced by an increase in potential energy or vice versa. So you can say this, I can change, there is no change, okay? So change in the kinetic energy plus the change in the potential energy is zero. Like our example, we saw that there is a change of minus 90 in the potential energy because final is 10, initial is 100, 10 minus 100 is minus 90. So the potential energy decreased, but it is accounted for by the same amount of increase, the plus 90 in the kinetic energy because 0 became 90. So the net change is 0. So we can write the law of conservation of mechanical energy in this form as well. Sometimes it is better to put it in this form because this quantity does not depend on where you choose the y equal to 0. All I need there is the delta y. Okay, right. Let's do this one, then I will stop. On the following slide are 5 graphs of energy versus vertical position for an object falling straight down from a given initial height. Which graph represents the potential energy, total mechanical energy, its kinetic energy? So neglect air resistance, that means we can say so it's an isolated system. The object and the earth, the system consists of the object and the earth and the object is falling. So we take this as our system. For that system, I can say mechanical energy is conserved, the total mechanical energy is conserved. Now with that, can we answer this question? Which one is represented by each of these graph? Which potential energy is represented by which graph, and mechanical energy, total mechanical energy is represented by which graph, and kinetic energy is represented by which graph? It's best to start with this. We know it's an isolated system, no non-conservative force, the total mechanical energy must be constant. So let me pick the total mechanical energy, C, right? Because it's a constant value, it's constant. So with y, okay, with the position. So for an object falling straight line. So the position is changing, the object is moving down. Say y is equal to some positive value, and it is coming down. So the object is falling, say down, let's say y equal to 0. Then it is further down. Let me put the y equal to 0 somewhere. So it will have a constant value and it will continue to have constant value. Even when it is at high positive value, it has certain value, then it will become the same value as the y decreases. Even when y is negative, it will be the same value. So it's very clear, total mechanical energy is C. Okay. What about potential energy? And what is the potential energy and what is the kinetic energy? There are two questions. So let's say we are dropping it from rest. What is the kinetic energy when we drop? No, answer my question. When you drop mean we release it from rest. What is its kinetic energy? 0. V equal to 0, kinetic energy is 0. So, and as the distance decreases, kinetic energy will increase, right? Okay. So it has to, for a high value of potential, y, it will have a certain kinetic energy and it will decrease. This looks like fine. But when it is passing 0, then it is increases. It is not decrease and increase, it's keep increasing, right? kinetic energy will increase as the distance become less and less, the height become less and less. So this is decreasing. It should increase, right? The kinetic energy should increase as the distance. This way, the distance decreases, right? So the kinetic energy should increase. You should have something like this. When at the highest point, it should be 0 because you are dropping, say, let's say this is y is equal to 10 meters. The kinetic energy is 0. And the highest value of y, the kinetic energy is 0. So this is not. What about this? Yeah, but there is a decrease again. It has to be keep increasing, right? The value should keep increasing. So it is this. This is possible. So we have at y is equal to high value, it is to have a 0 kinetic energy. So it's keep increasing. So this is the potential kinetic energy. Let me forget about the kinetic energy. Let's look at the potential energy. What do you think? Because potential energy has a nice equation. The potential energy is equal to kinetic energy. We don't have an equation as a function of y, but the potential energy is this. So potential energy versus distance has to be a straight line. When the distance increases, potential energy will increase. High distance, a large distance, it should be large potential value. Smaller vertical position will give you a smaller. So, this is linear. And when y equal to 0, the potential energy is 0. So this is clearly for potential energy. And then obviously this has to be the kinetic energy, because the potential energy plus kinetic energy should give you a constant. So that is what is going to happen here. So if it is kinetic at this point, let's say this is 100 joule potential, kinetic energy will be 0 at that point. So it is 100 plus 0, you have 100. So you got this line for the total energy. Okay, you're adding this value with that value, you get 100. So for another value of y, let's say, say 5 meters, so this is 10 meters, then you have the potential energy, let's say 50, but then kinetic energy will also be 50. So the total energy 50 plus 50 will be 100. Again, the total energy will be 100. So as the potential energy decreases as the object going down, kinetic energy will increase, keeping the total energy constant, giving the graph C for total energy. So the potential energy is E, kinetic energy is D, and the total energy is C. Okay, any question, please? Online? Any question? Is there anything
Doctor,
not clear? Yes,
can you repeat the answer?
I will repeat the answer. Okay, let me clear everything. Okay, now let me start with the potential energy. I'm going to repeat the whole thing. So I'm telling this is the potential energy. I'm going to explain it why it is so. Potential energy is given by mgy. So the potential energy versus y has to be a straight line, and it has to go through 0, 0. Because when y is equal to 0, potential energy is 0. Okay, Eileen? And it should be a straight line too. So there is no doubt when initially it is say 10 meters, okay, then it has a certain potential energy. Let me just take a number 100 joule. So as the position decreases, say 9 meter, the potential will be, let's say, 90 joule. Then and so on. At 0 meters, the potential will be 0. So when it is negative minus 10, the potential will be say -1 meter, the potential will be say -10 joule and so on. So this line is the only line that can account for the equation of the potential energy. Eileen? I need,
Yes, it is clear.
okay, fine. Decrease but linearly, and it has to go through 0, 0 also, right? The only line, only graph that can account for the potential energy is E. Okay, fine. Then let's go to the total energy. Total energy has to be constant. So the only line that can account for the total energy is C. Total energy is the potential energy plus mechanical energy. So this is the total energy. So when it is 100, so, and you also know at the top position, when it is 10 meters, we said the total energy is 100 joule. The potential energy is 100 joule and the kinetic energy is 0. So at 10 meters, so this is the 10 meters. This is the 10 meters. The kinetic energy has to be 0. So this is the only place where, this is the only graph which gives you at 10 meters, the kinetic energy to be 0. So this must be the kinetic energy. And also, we are getting that when it is dropping by a certain amount, the kinetic energy is increasing by the same amount. The potential energy dropped by say 10 joule, the kinetic energy will increase by 10 joule. So it has the same steepness but negatively. The potential energy and this has the same steepness or the same slope but negatively. Okay, Eileen? Okay, thank you. All right, I'll stop here. We got some more slides, but I will reserve it for the next class. Okay. All right, so it is Munira and Kazi. Okay. Thank you very much. We still have time, but it's fine.